Welcome viewers. In this video we'll see an introduction to the tuned circuits. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll see the topic tuned circuit and introduction. Tuned circuits are two types are available: single tuned and double tuned. The coupled circuits are mainly used to transfer the energy from weak source to a load or employed for maximum power transfer from one circuit to another circuit. So this is possible only when both the coils are at resonant condition. So the tuned circuits are framed from the coupled circuits. Coupled circuit means inductors are coupled together. So this coupled circuit mainly used for energy transfer from weak source to the load or maximum power transfer from one circuit to another circuit. In that case, both the coils, that's tuned means coupled circuit means inductors. In that the coils are resonant condition. Then only it is possible. Now we'll see the further details. In coupled circuit, the coils in which the source is connected is called primary, and the coil in which load is connected is called secondary. Two coils available. The coil connected with the source is called primary. The coil connected with the load is called secondary. The coupled circuit can be brought to resonance by adding capacitors to both primary and secondary. So we know that we need to go for the resonant condition. So that can be done by adding the capacitors on both primary and secondary of the coils. When the primary inductive reactance is very low or negligible, then it is sufficient if we resonate the secondary coil alone by adding the capacitor to the secondary coil to achieve the maximum power transfer condition. So the inductive reactance is very low means or negligible means it is sufficient if we resonate the secondary coil alone by adding the capacitors. Suppose when capacitor is added only to the secondary coils are called single tuned coupled coils, and the resonant resultant circuit is called single tuned circuit. So here what we are having the concept means the inductive reactive is very low or negligible, then it is sufficient to resonate the secondary coil alone by adding the capacitor to achieve the maximum power transfer condition. So in this case, when the capacitor is added only in the secondary coil, then it is called single tuned coupled coil. The circuit is called single tuned circuit. Then we will see the double tuned circuit. When the capacitors are added to both secondary and primary, the coupled coils are called the double tuned coupled coils. The resultant circuit is called a double tuned coupled circuit. So by adding the capacitor in primary and secondary, we can get the resonant condition. If we add the capacitor only in secondary coil, then it is called single tuned circuit. By adding capacitor both in primary and secondary, then it is called a double tuned coupled circuits. Now we'll see the further details. Normally in double tuned circuit, the primary and secondary are tuned at same frequency. So that is called a resonant condition. So both should be tuned at the same frequency. But in some time, intentionally, the primary and secondary are tuned at slightly different frequency. Practically, there may be some slight difference in the frequency of primary and secondary. Such a double tuned circuit is called a stager tuned circuit. So one special case is there. Normally the frequency of both primary and secondary are same, but intentionally primary and secondary are slightly different frequency. Such double tuned circuits are called a stager tuned circuits. So in this video we discuss the introduction about the tuned circuit. What are the types available? What are the uses of tuned circuit? How we are getting the tuned circuit type single tuned and double tuned, and what is the stager tuned circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the single tuned coupled circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Single tuned coupled circuit. We know that coupled circuit is nothing but inductance. It is inductively coupled together. In that single tuned means the capacitor is connected at the secondary side. It's called single tuned. This capacitor is connected in both primary and secondary side. In order to tune the circuit is called double tuned circuit. So this is coming under single tuned circuit. Capacitor connected only at the secondary of the circuit. Let us consider this is the parallel resonance circuit having primary and secondary coils are available. The parallel resonance circuit on secondary is inductively coupled to coil 1. These two coils are inductively coupled. The coil is excited by the source EG. The primary coil is excited by the EG. RG be the source reactance. RG is the source reactance. So we have the one resistor available here. Capacitor is connected in order to tune the circuit. This current I1, current I2. M is the mutual inductance between L1 and L2. EG source is the source given by EG. RG is the source reactance. The dot is available here. See the dot. The current enters in the dotted end in the first coil. Similarly, current leaves the dotted end in the second coil. So both are different. Current enters in coil 1 at dotted end. Current leaves the dotted end in the coil 2. So the self-inductance and mutual inductance are negative, opposite to each other. This is called a parallel opposing. Because of this dot rule, we can easily identify. In order to, this is the coil 1, coil 2. E0 is the voltage across the capacitor. So we are going to tune the circuit so that it is called a single tuned circuit. Now we need to go for the mesh equation. By using KVL, we need to frame the equation for coil 1 as well as coil 2. So these equations are available here. So we know that the KVL, the applied voltage equal to drop across the resistor and inductor. So EG is equal to drop across this RG, drop across R1, drop across L1. Similarly here also. That is voltage rise equal to voltage drop. So based on that, EG equal to, in coil 1 the EG is available. EG equal to I1 RG. Current in the first coil is I1 into RG minus, because this mutual inductance is and self inductance are opposing each other. So minus j omega m I2. Right. So I1 RG minus j omega m I2. Mutual inductance due to the secondary coil current. So that it is I2 equal to EG. Right. Minus omega as for the second circuit. Minus omega m I1. For second coil, mutual inductance due to the first coil. So that I1. Plus R2 plus j omega L2 minus j omega by minus j by omega c into I2 equal to 0. Right. So this is the equation 2. So this RG is very much higher. So that we are neglecting the R1 as well as L1. This R1 and L1 is neglected because RG is, we assume that RG is much more higher. So that EG equal to drop across RG minus drop across mutual inductance. In secondary coil, the voltage is not available 0. So the drop across mutual inductance, R2, L2 and capacitor. So all are available, R2, L2 and capacitor. Here R1 and L1 is neglected. Right. Now we'll go further. So these were two equations. Right. We are going to further simplify these equations. Now we'll go for the further details. So the assumptions are available here. Let R1, R2 be the resistance of coil 1 and 2 respectively, and L1, L2 be the self-inductance of the coil 1 and 2 respectively. So the assumption is available here. Assume that Rg is much more greater than R1, much more greater than j omega L1. So Rg is much more greater. So ignore R1 and j omega L1 in comparison with Rg. So that while framing the equation, we are not consider R1 and omega L1. So based on that, the mesh equations are reframed. Now consider the equation 1. I1 Rg minus j omega m I2 equal to Eg. R1 and L1 is not considered. Bring this term that side. So then minus become plus. Now bring this Rg in the denominator. So that we got the expression for I1. Eg plus j omega m I2 divided by Rg. So expression for I1. Now we'll go for the further simplification. So this is the equation 2. Now we'll consider equation 2 minus j omega m I1 plus R2 plus j omega L2 minus omega by j by omega c into I2 equal to 0. From equation 1 we got the expression for I1 that we are going to substitute in the second equation. So this I1 is replaced by the inside equation 2, this I1 is replaced by this equation. Now we can multiply inside minus j omega m Eg by Rg minus j available 2 times j square omega square m square I2 divided by Rg, and this term is available I2. Now this j square is minus 1, j square value is minus 1. So we will go for the further simplification. So minus become plus, it become plus, right. Now we'll take the I2 outside. So I2 available here as well as these two term having I2. So I2 is taken outside, and here one more term is available. That term is brought to that side. So it become plus, minus become plus. Now bring this term in the denominator. So that we got the expression for I2. From equation 1 we got the expression for I1. From equation 2 we got the expression for I2. Right. Now we'll go for the further simplification. So this Rg is multiplied inside. So that this Rg got cancelled. Plus Rg into this term. This term is available. So what happened? Omega square plus m square and this term. Right. So we got the I2 value. So for more further simplified, and we got the expression for I2. Now we'll go for output equation, output voltage. The output voltage E naught equal to I2 into minus j omega c. So this is nothing but the voltage across the capacitor. The current in the second coil is I2. The drop is minus j by omega c. Now we substitute the value. This multiplied and divided by j. So what happened here? This j become j square minus j square I2 divided by j. This j is divided here into omega c. We know that j square is minus 1. Already one minus is there. It become plus. So I2 divided by j omega c. In order to bring the j in the denominator, we are multiplied and divided by j. Now I2 minus j omega c now become I2 divided by j omega c. Here negative now become positive. Now we'll go for the further simplification. So E naught equal to I2 divided by j omega c. Split the terms. 1 divided by j omega c into I2. Now we can substitute the value of I2 here. This is the value of I2. In that this j and omega got cancelled. So that what we have Eg into m divided by this c, and the remaining terms are available. Take this equation number 4. So now we got the expression for output voltage E naught. I1, I2 values are already available. Now we got output voltage E naught also. From that we can go for the amplification factor. So the output voltage, output transfer function equal to out voltage amplification. That is A equal to E naught divided by Eg. So that is equal here. The Eg is available here. So Eg available, this Eg is brought in the denominator. So it becomes Eg naught, E naught divided by Eg. That is equal to M divided by this term. Right? So this Eg is brought to denominator this side. So that E naught divided by Eg, that is nothing but amplification factor. So now we got the expression for amplification factor also. From the output voltage equation we got the amplification factor. Now we'll see. When the secondary side is tuned, that is when the values of the frequency omega is such that, so what is the tuning of the circuit? Omega L2 is equal to 1 divided by omega C. So both are equal means the circuit is tuned together. So brought this term this side in the, so that omega L2 minus 1 divided by omega C equal to 0. So under the tuned condition, this expression is 0. So they are available here. Omega j omega L2 minus j by omega. So this term become 0 under the tuned condition. So that this equation 5, based on the above expression, the equation 5 becomes, so this term becomes 0. So what we have, M divided by C omega square plus M square plus Rg into R2. This term become 0. Under tuned condition it is 0. So now the amplification function is further simplified. That is under the tuned condition. This amplification factor on tuned condition. You take this equation number 6. Now we'll go for the further discussion. Omega L2 is omega 1 divided by omega C. So multiply this omega into omega, bring this omega here, L2 in the denominator, that's it. So omega into omega equal to 1 divided by L2 into C. So omega square equal to 1 divided by L2 C. This now become resonant frequency, because under resonant condition only this is occurs. So now omega square become omega R square. Right. From equation 3, the current I2 at resonance is obtained by putting omega L2 equal to 1 divided by omega C and replacing omega by omega R. So we already got the expression for I2, I1 and E0. Now we are going to obtain the same. We are going to further simplify the expression under the resonant condition by putting this condition. That is, otherwise omega L2 minus 1 divided by omega C equal to 0, and also replace omega by omega R. Right. So first we will see the current. This is the current, equation 3, this is the current expression. Here under resonant condition this term become 0. So that what we have, j omega R, omega become omega R, M E G divided by R G, omega square M square divided by R G plus this R2. This term become 0. Under resonant, we already know that under resonant condition this term is 0. So I2 at resonant is, this is the expression for I2 at resonant. Earlier what we got, I2 is the normal I2, the current in the second coil. This is the current in the second coil under the resonant condition. Now we'll go for the further simplification. So I at resonance, this Rg is multiplied inside, though this Rg got cancelled. Finally we got I2 at resonance is equal to j omega R M E G divided by omega square M square plus Rg into R2. So this is the current at the resonance, current I2 at the resonance. So from equation 6 and 7, it is observed that at resonant frequency E0, I2 and A are depends upon the M, that is mutual inductance, amplification factor, secondary current, output voltage. These three are depends upon the mutual inductance M. The maximum value of E0 or A depends upon M. So if you want to find out the maximum value of output voltage or amplification factor, means that is depends upon the M value. So that to get the condition for maximum E0, we need to differentiate the equation E0 with respect to M, because E0 is depends upon mutual inductance. Then by equating the 0, we will get the condition for maximum output voltage. Maximum output voltage depends upon A, m, so that it is differentiated with respect to m, but the E naught is differentiated with respect to m and equated to 0 to get the maximum value for E naught. Now we'll see, now we'll substitute the E naught value. So d by dm E naught equal to 0. E naught is nothing but EgM divided by C of Rg R2 plus omega R square into m square. Now we need to differentiate this term with respect to the m. M available in numerator as well as the denominator. So we can use the formula u by v method. This is u and this EgM is u. This term available in the denominator is the v. What is the formula differentiation? V du minus u dv divided by v square. V into differentiation of u minus u into differentiation of v divided by v square. So this is the term u and this is the term v. Now we'll go for first substitute the v. This is the v. Then du. So I see u, we have to differentiate with respect to m. So m divided by c, while differentiating this m is equal to 1. Differentiation of dm is 1. Differentiation of x is dx. Integral dx is x. Similarly here this dx, m is the differentiation of m is 1. So Eg divided by c into 1 minus u. The term u is substituted as it is. Then dv, we have to differentiate this with term v. So here this term is constant, so it becomes 0. Here m square is available, differentiation of m square is 2m. Then that is equated to 0 divided by v square. This is v square. Now we'll go for the further simplification, so that we'll get the condition for maximum output voltage. Right. So this term is Eg divided by c minus this term is 0, so that we have 2m into omega r square divided by v square. This v square is equal to 0, so this term, while multiplying this term with 0, it becomes 0 only. So after that we got this expression. Bring this term that side, so that negative become positive, it become plus. Now Eg available on both the sides. Eg available, C also available on both the sides, so got cancelled. Rg R2 plus omega R square m square equal to 2m square omega r square. So these two terms are very similar, so brought this term that side, so that it become negative. So 2 times m square omega r square minus 1 times omega r square m square, so it become 1 time. Right. I will go for the further simplification. So that Rg R2 equal to m square omega r square. Bring this omega r square in the denominator, this side, so that m square Rg R2 divided by omega r square equal to m square, so that m equal to Rg R2 divided by omega r square. Now take square root on both the sides, so that m equal to square root of Rg R2 divided by omega r. So this is the value we got. So when m equal to square root of Rg R2 divided by omega r, the output voltage is maximum. So this is the condition. dm, d E naught divided by dm is equated to 0. At the time we got this expression m. So this is the value at which the output voltage is maximum. So by substituting this m equal to this value, we will get the maximum output voltage. Now we'll see how we are getting the maximum output voltage. So this is the expression for output voltage E naught, EgM divided by here. So here we need to substitute m equal to Rg, square root of Rg R2 divided by omega r. So that is the condition at which it is maximum. Similarly, this here also it is substituted m square. But this term at the resonance, this term is 0. Omega j omega L1 L2 equal to minus j equal to j omega c. So when brought this side, this term is 0. So that Eg square root of Rg R2, this omega r is available in the denominator, right? C into omega r. Then this term is available. While taking the square, it become Rg R2. Square root of Rg R2 square is Rg R2 divided by omega r square into omega r square. Now everything is converted. Omega is changed into omega r, resonant condition. This term is 0. So Rg plus Rg into R2. This omega r got cancelled. So what we got finally? Eg square root of Rg R2 divided by C omega r 2 Rg R2. So that is nothing but Eg. So here the square root of Rg R2 available, here Rg R2 available. So we can write like this. For example, the root 3 can be written as multiply and divided by another root 3. So what happened? Root 3 into root 3, 3 divided by root 3. So based on that we can have this formula, right? Square root of Rg R2. So finally we have Eg divided by 2C omega r into square root of Rg R2. So this take equation number 9. So this simplification based on root 3 divided by 3 is available. This root 3 divided by 3 can be written as root 3 into root 3. So this root 3 got cancelled. We have 1 by root 3. Not based on this. This is based on this expression. Root 3 divided by root 3. So square root of Rg R2 is root 3. Rg R2 is the 3. Right? This 3 can be written as root 3 into root 3. Root 3 into root 3 is again 3. So this root 3 got cancelled. We have 1 by root 3. Rg R2. Now we'll go for the further simplification. Now we'll see the maximum amplification. So far we got the maximum output voltage E0. So this is the expression for amplification. In that we substitute m equal to root 3 into root 2 divided by omega r. If you substitute that value, we will get the maximum amplification, right? So this m is not replaced. Only this m is replaced by square root of Rg R2 divided by omega r, right? So we'll go for the further simplification. Square root of Rg R2 omega r into C Rg R2. So here also now substituted square root of Rg R2 divided by omega r the whole square. Now we'll go for the further simplification. So square root of Rg R2 omega rc into Rg R2 plus omega r square. It is while square taking square root, this square root become normal Rg R2 divided by omega r square. This omega r square got cancelled, right? So we have this is Rg R2, this is also Rg R2. So 2 times, we have 2 times available. Square root of Rg R2 divided by 2 times of Rg R2 and omega r c, right? Similar, very similar to previous case. The square root of Rg R2 divided by Rg R2 can be written as 1 divided by square root of Rg R2. So this is the maximum value of amplification. Am is nothing but 1 divided by 2 omega rc square root of Rg R2. Now we'll see the maximum value of the current. By using the same procedure, you can find the maximum value of current. So this is the current expression. In that we are going to substitute this 2m, we are going to replace square root of Rg R2 divided by omega r. So here also, right, here square is there. So while taking the square, it become Rg R2 divided by omega r square. This omega r square got cancelled. So finally what we have? J Ej Rg square root of Rg R2 divided by 2 Rg R2. Very similar to root 3 divided by 3. It is 1 divided by root 3. Like that, Eg divided by 2 square root of Rg R2. So this is the value of maximum value of current by substituting the m. So we calculated the maximum value of the m, the condition for maximum. For that we got the expression for m, mutual inductance. That is substituted in 3 different parameters. Output voltage E0, amplification A, and current I2. So that we got the maximum value of output voltage E0, maximum value of amplification, and maximum value of the current I2. Now we'll go for the further. These maximum values are obtained by substituting m equal to square root of Rg R2 divided by omega r in expression E0 A I2 at resonance. So we know that m equal to k square root of L1 L2. by changing the coupling factor K, we can vary the M. This variation of amplification factor or output voltage with the coefficient of coupling. So by changing the K, we can change the M value. So that this variation can be done by changing the coupling of coefficient of coupling, this K value. So these three are based on the M, but M is based on the K value. So by changing the K value, we can vary the amplification factor with the coefficient of coupling. So based on that, the graph is available. So x-axis is the resonant frequency, y-axis amplification factor. So this is the for different coupling coefficient of coupling, right? So these maximum values depends upon the mutual inductance M, but mutual inductance based on coefficient of coupling. So for the different values of coefficient of coupling, the graph is obtained. So K equal to here K1. K1 is maximum. K2 is less than K1. K3 is less than K2. So accordingly, we got the amplification also. K1 is the maximum value. We are getting maximum amplification. K2 is lesser. So the amplification factor also lesser. K3 is very lesser. So that amplification factor also lesser. Right. So when K value increases, the amplification factor also increases. Initially it is slowly increases. At this point reaches maximum, thereby decreases. For different values of coefficient of coupling, we got the different curve, right? When the coefficient of coupling increases, the amplification also increases. So in this video, we discussed the single tuned coupled circuits connecting capacitor at the secondary circuit in order to tune the circuit. We got the expression for E0, I2 amplification factor, thereby maximum value of these three parameters. Finally, we draw the graph also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the details about double tuned coupled circuits. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Double tuned coupled circuit. Let us consider this circuit. Two inductors are mutually coupled together. So this is called a coupled circuit. Tuned circuit means bring the circuit into pure resistance by making inductive reactance equal to capacitive reactance. So that both got cancelled, the circuit acts as pure resistance. In this, the double tuned means the capacitor. The tuning is done by the capacitor connected in primary circuit as well as secondary circuit. Single tuned means capacitor connected only in secondary circuit. So double tuned coupled circuit means two inductors are mutually coupled together, that is tuned by the capacitor connected in both primary as well as secondary side. So consider this circuit, two inductors are coupled together. Resistor and inductor value is R1, L1, here R2, L2, dot is available here. Energized, primary coil energized by the AC source, EG. The secondary coil we have output voltage, E0. The capacitor C1 connected in primary, C2 connected in secondary. RG is the source resistance. So this is the current direction, I1 in the primary side, I2 in the secondary side. M is the mutual inductance between L1 and L2. In first coil, the current enters in the dotted end, but in second coil, current leaving at the dotted end. So the self-inductance and mutual inductance both are opposite to each other. Parallel opposition, because current enters at dotted end in coil 1, current leaves at dotted end in coil 2. So both are opposing. L and M are opposing. It is coming under parallel opposition method. Now for the circuit zone, we consider a special case where the primary and the secondary resonate at the same frequency. Both primary circuit or secondary circuit is resonated at the same frequency, that is omega R, that is equal to 1 divided by L1 C1, that is equal to 1 divided by L2 C2, right? So both the circuits resonate at the same frequency. Now we are going to apply the mesh equation, Kirchhoff's voltage law to frame the equation for both primary coil and secondary coil. Right. So what is the mesh equation? The applied voltage E equal to drop across resistor and inductor and capacitor. That is the Kirchhoff's voltage law. This is voltage rise equal to voltage drop. Right. So in the first circuit we have the voltage source EG. EG equal to the drop across this RG, C1, L1 and R1. All these four elements are available. That is by the current I1. RG plus R1 plus J omega L1 minus J omega C1. These four elements are available. RG, R1, C1, L1. Then we go mutual inductance available. Mutual inductance due to the secondary coil. So it is multiplied by I2. We already know that both are opposing, parallel opposition. So minus omega M I2. So this is coming under reactance, impedance, resistant, capacitor and inductor. This is coming under mutual inductance M. That is opposing, so negative sign. That mutual inductance in first coil is due to the second coil, so that it is multiplied by I2. I will take this equation number 2. This is equation number 1. We will go into the second coil. First we will see the mutual inductance. Mutual inductance in second coil is due to the first coil, so minus J omega M I1. Right. So it is also opposing, so the negative sign, plus I2. Here what are the elements available? R2, L2 and C2. These three elements are available. So R2 plus J omega L2 minus J omega J divided by omega C2 equal to 0. Here there is no source available. So equal to 0. So these two, they take this equation number 3. So this is the equation number, third equation, equation number 3. So we framed the equation. Now we need to solve this equation in order to identify the I2, current I2, because we need the value of E0, output voltage. Output voltage is nothing but C2 into I2. So that we need the value of I2. So we will go for the matrix format. The given equation now converted into matrix format. So what is the matrix? V equal to I into R. This is the voltage matrix, current matrix and the impedance matrix. Right. So the same equation we can write. So this term is nothing but R11. What is R11 or Z11? The impedance available in the first loop 1. This is Z22, this term. Impedance available in the second loop. This is nothing but Z12, this is Z21. That is the impedance available commonly between loop 1 and 2. So this mutual inductance is available between the coil 1 and 2. So minus J omega M, here also minus J omega M. Otherwise we can write the equation as it is. So this is Z11 impedance in the first loop, Z22 impedance in the second loop. This is the Z12, Z21. The current is I1, I2, the voltage is first loop EC and second loop is 0. Then how to find the I2 value? I2 equal to delta 2 divided by delta. What is the delta? This is delta. Determinant of this matrix is the delta value. Delta 2 is replace the second column with the voltage matrix, that will give delta 2. So first we will find the delta. So this is the delta. We need to multiply these two terms minus these two terms, so that we'll get the value of delta. Now we'll go for the multiplication. So these two terms are multiplied, minus of j omega m into minus of j omega m. Right. Now we'll go for the further simplification. Here j into j become j square. Here minus available, here also minus available, so it become plus. J square value we know that minus 1. So minus into minus become plus. So this is the delta value. Right, only here we simplify. J minus j into minus j is j square. J square value is minus 1. So it become plus. Now we'll go for the further simplification. Now we'll find the delta 2 value. Delta 2 means second column is replaced by voltage matrix EG and 0. Now we have to cross multiply these two. While cross multiplying, it become 0. Now these two, minus of Ej into minus j omega m. Minus into minus become plus. So that Eg j omega m is the delta 2. So that we can easily find the I2 value. I2 equal to delta 2 divided by delta. This is the delta 2 value. This is delta value. Right. So now we got the expression for I2. Now we'll go to the resonance. The case for the resonance. What happens if it is resonance? So this I2 is taken as the equation number 4. At resonance, omega r equal to 1 divided by square root of L1 C1, that is equal to square root of L2 C2. Right. Now at this condition we'll find the current I2. Hence at resonant current at the resonant I2 equal to this value. What happened here? In the equation number 4, these two at resonant, these two are equal. So omega j omega L1 equal to j divided by omega C1. So that j omega L1 minus j divided by omega C1, this term become 0 at the resonance. Similarly here also it becomes 0. So j Eg omega m divided by R2 R1, right, this term is 0 plus omega square m square. Only these two terms are available. So this take equation number 5. So we'll take this equation number 5, right? So here this term becomes 0, so that Rg plus R1, this term becomes 0, so only R2 plus omega square m square, right? Now we can go for, now we calculated the resonant current and the resonant condition. Now we'll go for the output voltage E0. E0 equal to I2 into j minus j divided by omega r C2. This is the voltage across the capacitor. Current is I2, the impedance is minus j divided by omega c I2. Now we'll substitute the I2 value. This is I2 value. So omega r dot cancel. Only these two terms cancel. Here minus j available, here j available. So it becomes minus j square EgM divided by the denominator term. Right. Now we'll go for the further simplification. J square value, we know that j square value is minus 1. So it becomes plus. Right. So bring this Eg in the denominator. E0 divided by Eg. Right. So here we do two things. One is minus j square. J square value is minus 1. So minus into minus become plus. Eg is brought to the denominator this side. So this Eg divided by E0 divided by Eg. Output voltage divided by source voltage is nothing but amplification factor. So that is m divided by C2 of R2 into Rg plus R1 plus omega square m square. Right. Now this is equation number 7. This is nothing but the amplification factor. So we calculated first the current, secondary current I2, then secondary current at the resonance. By using that I2 we calculated the output voltage E0. From that we calculated the amplification factor. Now we'll go for the maximum value. The maximum value of A, that is amplification factor, or maximum value of E0 can be obtained by taking the first derivative of A or E0 with respect to m and equating to 0. Right. So now we are going to find the maximum condition for maximum value of amplification factor and output voltage E0. So that it is mainly depends upon the mutual inductance. In both the cases mutual inductance is dependent. So that dE0 divided by dm is equated to 0. Differentiate with respect to mutual inductance of E0 and equating 0 will get the condition for maximum output voltage. Similarly, differentiate with respect to mutual inductance of A, amplification factor, and equating to 0 will get the condition for maximum amplification. So this is coming under maximum theorem. Maximum theorem means we have to differentiate the term with respect to the particular parameter. Here the parameter is mutual inductance, and equating to 0 will get the condition for maximum value. Similarly, here we can get the condition for maximum amplification and maximum E0. Now we'll go for the derivative. Now we'll derivate this and equate it to 0. So now we'll differentiate the amplification factor with respect to the mutual inductance dA by dm and equated to 0. So d by dm of the expression for amplification factor is this m divided by C of R2 in R2 of Rg plus R1 plus omega R square m square, that is equal to 0. Now we need to differentiate with respect to mutual inductance m. M is available in numerator as well as the denominator. So we can use the U by V method. So this term M by C is the U. This remaining term is the V. U and V terms are there. What is the formula differentiation of U by V? V du minus U dV divided by V square. So this is the formula. Now first we will substitute the V here. So this term is V into du. U is M by C. So du is 1 by C. Differentiation of dm is 1 minus U. U is M by C into dV. dV is, this term is constant, becomes 0. Omega are also constant. Differentiation of 2m is, m square is 2m. So that is equal to 0 divided by V square. Now we'll go for the further simplification. So here so that is equated to 0. This the term available in the denominator also becomes 0. Only the term available in numerator is available. Right, here C is there, that is 1 divided by C. R2 of Rg plus R1 plus omega R square m square divided by C minus m by C is there. M divided by C, here m, here also one m is there, so m square, this 2 is available, omega R square divided by C, this term is available in the denominator. The total term in the denominator is becomes 0, only this numerator is available, that is now simplified. The C is available commonly, so we will take the LCM. So R2 of Rg plus R1 plus omega R square m square minus 2 m square omega R square. Right. So this C also now become 0. Only this term is available. Right. So omega R square m square minus 2 omega R square m square. 2 times available. Both are same term. So 1 minus 2 is 1. Right. So omega R square m square minus 2 omega 2 m square omega R square is m square omega R square. That is equal to 0. Now we will go for the further simplification. Bring this term that side, so this negative become positive, right, and bring this term in the denominator, bring this term, right, what we need is m square, so bring this term in the denominator of that side, so that m square equal to R2 into Rg plus R1 divided by omega R square. This term is brought into the denominator of that side. So m square, so m by taking square root on both the side, it is square root of R2 of Rg plus R1 divided by omega. Here omega R square is there, omega R. This m become now mc. This mc is nothing but critical value of mutual inductance, right? Because it is differentiated with respect to m and equated to 0. So we will get the condition for maximum amplification. So at this value, the mutual inductance become critical mutual inductance. The amplification factor become maximum. By substituting this value, we will get the maximum amplification factor. So that this m become mc, critical value of inductance. The maximum value of E0, I2 are obtained by substituting the value of mc in equation E0 and I2. So by substituting this mc, we can get the maximum value of E0 and I2. Now we will go for the maximum. We'll find the maximum value one by one. So now first we will find the maximum value of output voltage E0. So this is the expression for E0. In that we are going to substitute m. Here m available, the two places. So m is replaced by square root of R2 of Rg plus R1 divided by omega R. So this is the condition we got by making by using the maximum value theorem. So here also it is substituted. Here square is there, m square. So what happened? This omega r brought to denominator. So Eg of r2 square root of r2 of rg plus r1 divided by c omega r into r2 of rg plus r1. Here square is there. So already one omega r square is there. This square root become normal r2 of rg plus r1 divided by omega r square. This omega r square got cancelled. Now we go for the further simplification. So Eg into this term available divided by c omega r. See, this term available 2 times, both are same. So 2 times of r2 divided by rg plus r1, right? So Eg divided by 2 omega c 2 c omega r, and this, what about this square root of r2 plus rg, both are same. Then how will you write this? This equation can be written as, for example, root 3 divided by 3 is there. Let us consider this is the 3. So by multiplying this root 3 divided by this 3 can be written as root 3 into root 3. So this root 3 got cancelled, become 1 by root 3. Right? So as like that it is 1 divided by r2 of square root of r2 of rg plus r1. Right? So root 3 by 3. This is root 3, this is 3. Right? And that this 3 can be written as root 3 into root 3. Root 3 into root 3 is 3. So this 1 root 3 got cancelled. Now we got 1 divided by root 3. Now we got the value of maximum value of E naught, that is equal to Eg divided by 2c into omega r of square root of r2 into rg plus r1. We'll take this equation number 9. Now we'll go for the maximum value of the current I2, secondary current I2. Maximum value of current. So this is the expression for maximum current I2. In that we are going to substitute here m, here also m square, right? Then it is, this square is there, this omega r got cancelled. Here we can go for the square. Here square root is there, so it become normal. This omega r square, both are got cancelled, right? This term available 2 times. This rg of rj plus r1 available 2 times. So here it is written 2 times. So Eg divided by 2, very similar to previous case. Root 3 divided by 3 can be written as 1 by root 3, right? So based on the same procedure, this is replaced. So I2 equal to Eg divided by 2 of square root of r2 of rg plus r1. We'll take this equation number 10. This is the expression for maximum value of current I2. So now we got the E naught, maximum value of E naught as well as I2. Now we'll go for the further analysis. So from the definition, mutual inductance equal to K into square root of L1 L2. K is the coupling coefficient. The coefficient of coupling K at M equal to MC. The mutual inductance become critical mutual inductance. At that time the K also become critical coefficient of coupling. So that it is given by MC equal to Kc into square root of L1 L2. The critical coupling causes I2 to have the maximum possible value. At resonance, the maximum value of A is obtained by changing the M or by changing the coupling coefficient for the given value of L1 and L2. So during the critical coupling, we are getting maximum value of I2. Similarly, the amplification factor. So the amplification factor, we can change M by MC and also K by Kc. Both are related. So by changing the coupling coefficient also, mutual inductance will changes, right, for a given value of L1 and L2. So in this video, I discussed the double tuned circuit, coupled circuit, the capacitor connected in primary side as well as secondary side. We started the mesh equation. We got the expression for I2. Then we got E naught output voltage. Then we got the maximum value of the I naught and E naught by making dA by dm equal to 0 and di2 by dm equal to 0. So that we got the expression for critical coefficient of coupling, critical mutual inductance MC. So that is substituted in I0, I2 as well as E0 in order to get the maximum value. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the solved problem based on the tuned circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic, tuned circuit solved problem 1. We know that tuned circuit is done by the connecting capacitor both in primary and secondary coil. If only connected in secondary coil is called single tune. Connected in both primary and secondary means double tune. That is, the reactive inductance is equal to reactive capacitance. So both got cancelled. Only the circuit behave like a resistance. That is called a tuned circuit. Now we'll see the statement of the problem. In a series fed doubly tuned transformer circuit, both the primary and secondary are tuned to the same resonant angular frequency of 10 to the power 5 radian per second. The maximum output voltage across the capacitor is 24 voltage and is obtained by varying the K. K is nothing but coupling coefficient. If the inductance and the resistance of the primary circuit are 4 microhenry and 0.1 ohm respectively, and of the secondary circuits are 50 microhenry and 1 ohm respectively. Calculate the supply frequency. We need to calculate the supply frequency. Now we'll see what are the data available one by one. So the resonant frequency is given for both primary as well as secondary side. Resonant frequency omega are equal to 1 divided by square root of L1 C1 primary circuit. That is equal to 1 divided by square root of L2 C2. So that is equal to 10 to the power 5 radian per second. So this data is available. Both are tuned at the same frequency. So we can use this expression to find the variables. And maximum value of E0 is 24 voltage. And L1 is given 4 microhenry. That is 4 into 10 to the power minus 6 Henry. L2 is 50 microhenry. 50 into 10 to the power minus 6 Henry. Rg is 0. The source resistance is not given, so assume to be 0. We need to find the source voltage Eg. R1 is given as 0.1 ohm, R2 is given as 1 ohm. Right. First, from the given data, the resonant frequency is given, so I will use this formula. 1 divided by square root of L2C2 equal to 10 to the power 5. Now square on both the side, so that 1 divided by L2C2 equal to 10 to the power 5 the square. Right. Now bring the C2 in the numerator, this side. 10 to the power of the whole square in the denominator, that side. So 1 divided by L2, 10 to the power 10. 10 to the power 5 square is 10 to the power 10 equal to C2. So that is C2 equal to 1 divided by L2. L2 value is given as 50 microhenry. 50 into 10 to the power minus 6 into 10 to the power minus 10. L2 value already available. So from that C2 equal to 2 into 10 to the power minus 6 farad. Otherwise 2 microfarad. Now the C2 value is calculated. Our aim is to find the source supply voltage Eg. Now we'll see how to find the supply voltage. So the maximum E0, maximum value of output voltage E0 equal to Eg divided by 2 omega R C2 square root of R2 into R2 of Rg plus R1, because the maximum E0 is given in the problem and other values also available. C2 also now we calculated, so that we can easily calculate the output voltage Eg. Now cross multiply this, all the terms multiply here, so that Eg equal to E0 into 2 into omega R into C2 of square root of R2 of Rg plus R1. All these terms are multiplied with the E0. Right. Now these all the values are available. Right. C2 just now we calculated. So E0 is given as 24 into 2 into the resonant frequency is 10 to the power 5. C2 what we calculated, 2 into 10 to the power minus 6 into square root of R2 is 1. Rg is not given, assumed as 0. R1 is 0.1. So by simplifying this we got 3.036 voltage. Now the in source supply voltage is calculated. So in this problem, we discussed the solved problem based on the tuned circuit. We calculated the supply voltage. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the tuned circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic tuned circuit, problem number 2. We know that tuned circuit is nothing but connecting the capacitor in the primary and secondary side, so that we have to bring the capacitive reactance equal to inductive reactance. Both got cancelled. So the circuit behave like a resistance. That is called a tuned circuit. If capacitor connected in secondary circuit called single tuned circuit, connected in both primary and secondary means it is double tuned circuit. Now we'll see the statement of the problem. In a series fed double tuned circuit, a maximum voltage gain of 20 was obtained at a resonant frequency of 10 to the power 6 radian per second. The capacitance in the primary circuit is 20 microfarad. The maximum output voltage at resonance is 50 voltage, right? So the voltage gain is given, resonant frequency is given, primary side capacitance is given, maximum voltage at resonance also given. We need to find the 4 parameters. First one is supply voltage. Second one, primary and secondary self-inductance, L1 and L2. The critical value of coupling coefficient, Kc. The fourth one is capacitance in the secondary circuit. Assume that the primary and secondary resistance are 1 ohm and 4 ohm respectively, right? Supply voltage, inductance L1, L2, critical coefficient of coupling Kc, and the secondary circuit capacitance C2. One more data available is R1 and R2. R1 is 1 ohm, R2 is 4 ohm, right? From the given data, we will calculate the parameters one by one. First, the maximum voltage gain is given. AM is 20. Resonant frequency omega is 10 to the power 6 radian per second. Maximum output voltage at resonance E0 is 50 voltage, right? So first we will see the use the formula. Amplification factor AM equal to E0 divided by EG. Output voltage divided by supply voltage, right? The AM value is given as 20. E0 maximum output voltage is 50. EG, from that we can easily calculate EG. Bring the EG in the numerator, bring the 20 in the denominator that side. So that EG equal to 50 by 20 is 2.5 voltage, right? So the supply voltage is 2.5 voltage, right? Now we'll go to find the L1 value. The C1 value is already given, 2 microfarad, that is 2 into 10 to the power minus 6 farad. So by using this formula we can find L1 value. C1 is available, omega R also available. So omega R equal to 1 divided by square root of L1 C1. Omega R is 10 to the power 6 equal to 1 divided by square root of L1 is not available. We need to find, and C1 is 2 into 10 to the power minus 6. Now square on the both the sides in order to get, so 10 to the power 6 square equal to 1 divided by, while taking square, the square root is disappear. So L1 into 2 into 10 to the power minus 6. Bring this L1 in the numerator of that side. Bring this 10 to the power 6 to whole square is new denominator this side, right? So that L1 equal to 10 to the power 12. 10 to the power 6 whole square is 10 to the power 12 into 2 into 10 to the power minus 6. So while simplifying we got 0.5 into 10 to the power minus 6. That is 0.5 micro Henry. So one parameter is calculated. L1 is calculated. Supply voltage calculated and L1 is calculated. Now we'll go for the another parameters. So next we will find the critical coefficient, maximum mutual inductance. From that we will find the maximum mutual inductance, MC. Thereafter we will find L2. So the MC equal to square root of R2 of R1 plus RG divided by omega R. So all the values are available. R2 is 4, R1 is 1, RG not given, say assumed as 0, omega R is 10 to the power 6. So the maximum critical maximum mutual inductance is 2 into 10 to the power minus 6 Henry. The critical value of mutual inductance, MC. Right. Now we'll go to the maximum output voltage. One more parameter is given. E naught equal to Eg divided by 2 omega R square C2 into MC. MC now we calculated. So in this all the values are known. Only C2 is not known. So we can easily find the C2. Bring the C2 in the numerator this side. E naught, bring the E naught in the denominator that side. So that C2 equal to Eg divided by E naught into 2 omega R square MC. See, all these values are known. We will substitute all the values. So 2.5, Eg is 2.5, just now we calculated, divided by E naught is given as 50 into 2, the resonant frequency 10 to the power 6 square, and MC what we calculated 2 into 10 to the power minus 6. So while simplifying we got 1.25 into 10 to the power minus 8 farad. So the C2 value is 1.25 into 10 to the power minus 6 farad. Now we calculated C2 also. Now we need to find the L2 value. L1 already calculated. Now we'll go for L2 value. So we'll use the same formula, omega R. But here L2 C2. Earlier we used L1 C1. Now C2 is calculated. So we can use this C2 here to find the L2. Earlier C2 is not available. Now C2 is calculated. Now square on both the side, omega R square equal to 1 divided by L2 C2. So L2 we need to find. Bring this L2 in the numerator this side, omega R in the denominator that side. So L2 equal to 1 divided by C2 into omega R square. Right. C2 what we calculated 1.25 into 10 to the power minus 6. Omega R is 10 to the power 6 omega R square. So while simplifying we got 80 into 10 to the power minus 6 Henry. That is 80 microhenry. Now L2 also calculated. L1 calculated, L2 calculated, C2 also calculated. And supply voltage supply voltage also calculated. The remaining one thing is critical coefficient of coupling, Kc value. We need to find the Kc value, one more parameter. Kc equal to MC divided by square root of L1, L2. So L1, L2 value is calculated. MC also we calculated. All the values are known. MC what we calculated is 2 into 10 to the power minus 6. Square root of L1 is 0.5 into 10 to the power minus 6. L2 what we calculated 80 microhenry. 80 into 10 to the power minus 6. So while simplifying we got 0.32. Critical value of coupling coefficient is 0.32. Now we calculated all the values. Supply voltage L1, L2, C2, MC value, then critical value of coefficient of coupling. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the tuned circuit. Problem number 3. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic tuned circuit, problem number 3. We know that tuned circuit means we are making the inductive reactance equal to capacitive reactance so that the circuit behave like a resistance, only the resistance. Single tuned means capacitor is connected in the secondary side in order to bring the resonant condition. Similarly, the capacitor connected in primary as well as secondary means double tuned circuit. Right, now we'll go to the problem. In the single tuned resonant circuit, the applied voltage in a primary coil Eg equal to 20 voltage. Rg is assumed as 0, source resistance. R1 equal to R2 equal to 5 ohm. L1 equal to L2 equal to 33 microhenry, 32 microhenry. Mutual inductance is 20 microhenry. The capacitance in the secondary side 0.5 microfarad. So the source voltage given, source resistance 0, R1, R2, L1, L2 values are available, mutual inductance available, the capacitor at the secondary also available. Determine the resonant frequency and the output voltage at this frequency. We need to find the two parameter, resonant frequency omega R and output voltage at this frequency E naught. Right. First we will find the resonant frequency. From the given data, we will find the resonant frequency. Omega R equal to 1 divided by square root of L2 into C. So these both the values are available. L2 is 32 microhenry, that is 32 into 10 to the power minus 6. C value is 0.5 microfarad, so 0.5 into 10 to the power minus 6. So by simplifying we got 0.25 into 10 to the power 6 radian per second. So the resonant frequency is calculated. So at this resonant frequency we will find the output voltage. At omega r the output voltage. The formula is E naught equal to Eg into M divided by C of R2 plus Rg plus R2 plus Rg into R2 plus omega R square into M. All these values are available. Eg is 20 voltage, mutual inductance 20 micro Henry, so 20 into 10 to the power minus 6. Capacitance is 0.5 microfarad, so 0.5 into 10 to the power minus 6. Rg value is 0, R2 is 5 plus omega R square, just now we calculated 0.25 into 10 to the power minus 6 square into M. 20, M is 20 microhenry, so 20 into 10 to the power minus 6. So by simplifying this, what we got, 0.64 into 10 to the power minus 3 voltage. The output voltage is 0.64 into 10 to the power minus 3 voltage. So in this problem, from the given data, we calculated the resonant frequency and output voltage at the resonant frequency, 2 parameters. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.